Welcome to video 4. Almost done. There are 5. So today we're going to talk about electron affinity. So the electron affinity is the energy associated with the reaction that looks like this. We are taking a neutral gas phase atom of a particular element. We are adding an electron to form a -1 ion, also in the gas phase. And the energy associated with that reaction is called the electron affinity of that particular element. For most elements, it's actually a fairly exothermic process. And now in this case, if you do this, you end up with a release of 328 kilojoules per mole. Now, a brief word of convention here. Elements that have large negative electron affinities are said to have large or great electron affinities. So there's a reverse between the English and the math. Now, I want to compare this with the first ionization energy. Now, these two are complementary processes, but they are not opposites. So to review, the first ionization energy of fluorine is said to be the energy associated with this reaction. We have the neutral gas phase fluorine atom, and it goes to a free electron and a gas phase fluorine plus ion, which is not something you usually see. It's not a particularly happy camper. That's why this requires the input of a mind-boggling 1681 kilojoules per mole. So they are not opposite. So both of these, just to keep things straight, always start with a neutral atom of that element. Now, there is one thing you can say, that for any element, for any one element, the absolute value of its electron affinity is going to be less than its first ionization energy, which is always less than its second, which is always less than its third. And more on these two in a bit. So let's just get right to it. So what is the trend for electron affinity? And what you see here is this is a fairly generous use of the word trend. Broadly speaking, electron affinities get larger as you go from the bottom to the top, and as you go from the left to the right. But there are quite a few breaks in that trend, and I use this as an illustration because it turns out if you look carefully at the electron configurations of these various elements, you can actually quite nicely describe the breaks in the trend. So the first one is probably the most glaring one. It's going from the halogens, group 7, to the noble gases, group 8. So the halogens are the elements that have the greatest electron affinities. And the noble gases have actually very, very low electron affinities. They're actually endothermic. You need to actually put energy in to them for them to take that electron. So think about the nature of that last electron that you put in. All of these halogens have the electron affinity, have the electron configuration ns2np5, where that n here represents the row number, so 2, 3, 4, 5, and so on. Adding an extra electron to form that -1 ion would transform them to having electron configurations ns2np6, which is a noble gas configuration. It is a completely filled shell. And we have told you in a few ways, almost since day 1, or day 2 actually, that these electron configurations are very stable. What we know now is that all of these, the noble gases, all have completely filled shells, which makes an atom very stable, which is why the halogens will do just about anything to get that extra electron. The noble gases, on the other hand, already have that complete shell. They already have configurations of ns2, np6 for their neutral atoms. And for them, the addition of an extra electron actually just makes matters worse, because that extra electron is going to be an s-type electron in the next shell up. So that electron is added to a higher energy shell, and so the whole process just isn't energetically favorable, which is why, well, they don't do it particularly easily. The other break in the trend that can be easily explained is for group 1 and group 2. Now, while these are not particularly large electron affinities, they're larger than their neighbors, and these, based on the overall trend, these should be larger. Why aren't these should be greater electron affinities? Why aren't they? Well, let's look at what's going on here. So when group 1, all the group 1 elements have configurations ns1, and if you add another electron, you go to ns2. And it turns out that completely filled subshells are also a good thing for your average atom to have. Group 2, on the other hand, already has a completely filled subshell. That extra electron goes into the p subshell right above it. And while this is not as bad as adding the new electron to a completely new shell, it's still energetically unfavorable. And so that is why the electron affinities for the group 2 elements are a little bit lower than you might otherwise expect. And these are a little bit greater than you might otherwise expect. And remember, we're reversing the math here. All right, the last blip in the trend you can see is when you're kind of going to these elements right here, right? And so the elements in group 5A have a slightly lower electron affinity than, again, you might otherwise expect. So why would that be? Well, so the group 5A elements, so nitrogen, phosphorus, arsenic, and such, they have electron configurations ns2 and p3. And adding that extra electron would produce a negative ion with the electron configurations ns2 and p4. Now, going from p3 to p4, what's going on there? Well, remember that fourth electron, or that specifically that fourth p-type electron, is the first one that is paired. And it requires a little bit of extra energy to flip the spin of an electron and put it in a region of space where there already is an electron, which is essentially what you're doing here. So that's why these elements have the electron affinity of these elements is a little bit less than you might otherwise expect, because you're adding an electron into an already occupied state, and that's a little bit less energetically favorable as well. So the moral of the story for electron affinity, trends are only approximate. Now, so what I want you to do is think about lithium, sodium, and potassium being put in water. Now, what I will tell you is that even though it's not a gas phase reaction, that the product in this reaction is a +1 ion, either lithium, sodium, or potassium plus. So think about what you know about ionization energies and electron affinities and see if you can figure out which one of these will have a more vigorous reaction with water. And then check out this video to see how good your guess was. And we will see you next time. One more video to go.